Alright everyone, and welcome back to the AI Research Roundup. I'm your host, Alex. Today, we're diving into a paper published March 21st, 2025, titled Decouple and Track, Benchmarking and Improving Video Diffusion Transformers for Motion Transfer. This research tackles the challenge of, motion transfer in videos. That's essentially taking the movement from one video and applying it to a new one, while making sure the AI can separate the motion from the subject's appearance. The authors introduce a new method called DeT, which adapts AI models known as Video Diffusion Transformers, or DITS, to get better at this. They also present a new benchmark, MT-Bench, and a new way to measure how well the motion is copied. And for those interested in trying out this DET method or the MT-Bench benchmark themselves, the authors have also shared their work on GitHub. This repository contains the code for their motion transfer approach, along with, example data, scripts for training and running the models, and even the tools for MT-Bench. Okay, so to give you a visual of what this DET method, which works by adapting video diffusion transformers, can do, Figure 1 here really shows it in action. On the top row for each example, you have a source video, like a woman riding a horse on the left, or a woman dancing on the right. The idea is to take the motion from that source video and apply it to a new subject in a new scene, say making a tiger jump like the horse or a gorilla dance like the woman. This figure compares DET with other approaches, and their DET method, shown at the bottom, seems to transfer the motion very effectively while also handling the new subject and background. The red boxes on the other methods highlight areas where those approaches didn't perform as well. Okay. So building on those visual examples, Figure 2 gives us a more quantitative comparison. This chart plots different methods based on two key metrics, edit fidelity, or EF, on the vertical axis, and motion fidelity, or MF, on the horizontal axis. Now, edit fidelity. That basically measures how well the AI keeps the appearance of the subject and the scene consistent after applying the new motion. And motion fidelity. That's about how accurately the original motion is copied. Ideally, you want to be in the top right corner of this graph, high on both. And you can see their method, labeled ours and marked with red stars, is right up there, indicating it strikes a really good balance between these two, outperforming other methods. Okay, so after seeing those overall scores in Figure 2, Figure 3 here, it kind of peeks under the hood to understand why their DET method performs well. It focuses on something called DIT features. Now, these video diffusion transformers we've mentioned, they internally process information about the video. And this information is captured as what the paper calls DIT features. Think of these features as, the key characteristics the AI learns to distinguish. For example, the moving person from the background, especially as things change over time, or across the temporal dimension of the video. The top parts, A and B, show generated frames and these feature maps, with their method in B showing a much cleaner separation. Then part C visualizes how these features evolve, and their approach, on the right, clearly distinguishes the foreground from the background much better than the standard video diffusion transformer on the left. Alright, so building on how DIT features are improved, Figure 6 details a key mechanism, the shared temporal kernel. Part A shows this kernel smoothing DIT features over time, which helps distinguish consistent foreground from the background. Then, Part B outlines its technical implementation. This involves a temporal 1D convolution, a method to process video by analyzing changes across time, and also a Gaussian error linear unit, or GLU activation function. This Gaussian error linear unit activation function is a rule that helps the model learn these complex temporal patterns effectively. So, we just saw in Figure 6 how that shared temporal kernel helps smooth DIT features over time. Figure 4 here. It really drives home why that kind of processing is crucial. It visualizes these DIT features again, but this time, it highlights a problem the paper calls entanglement. You can see the original video frames at the top with a person dancing. Below that, the corresponding DIT features are shown. The issue highlighted is that in some frames, the features for the foreground person and the background become inconsistent and then indistinguishable. Essentially, they get tangled up, making it hard for the model to properly separate the subject's appearance from its motion. Okay, so given that problem of feature entanglement we just saw in Figure 4, Figure 5 now looks at frame-to-frame attention maps. These maps essentially show which parts of other video frames the model focuses on when processing a particular frame to understand how things are changing. What's really interesting here is that the significant values, the bright areas, appear mainly along the diagonal when comparing adjacent frames. This indicates the model primarily tracks changes in those DIT features by looking at the very next or previous frame, suggesting a local temporal understanding or a narrow window of time is what's most active. So after seeing how models track changes frame by frame in those attention maps, Table 1 here, it shifts focus to how we actually test these models. It's a benchmark comparison. A benchmark in AI research is like a standardized test, a collection of videos and tasks to see how well different models perform against each other. Their new benchmark, called MT-Bench, is shown on the far right. It features 100 videos and 500 prompts, which are the text instructions given to the model. Noticeably, MT-Bench aims for higher difficulty, including hard scenarios, and has the largest num clusters at 6.31. This num clusters value likely indicates a greater variety or complexity of motions and scene types within the benchmark, making it a more comprehensive and challenging test for these video generation models. So we've seen how MT-Bench, their new benchmark, really pushes the boundaries for testing these video generation models. Ultimately, this paper highlights key challenges like feature entanglement and offers ways to improve how models track motion over time. This is super important for creating more realistic and controllable video generation. That's all for this AI Research Roundup. Thanks for tuning in. I'm Alex, and I'll catch you next time.